Okay, like with confidence intervals, you can use the z-distribution to calculate hypothesis tests for proportions. And the only thing that changes is the standard error calculation in the test statistic. Let's take a quick look at the formula. You have the test statistic, in this case z instead of t. You have the difference between the sample proportion and the hypothesized population proportion, and then you divide by the standard error. And after that, the steps are the same. You calculate the p-value for the test statistic, and then compare that to alpha. Quick reminder though, both p times n and 1 minus p times n, p being the sample proportion, must be greater than 5 for the central limit to apply. Alright, time for your next assignment on hypothesis tests. Nick is back with another email on student salaries, so let's see what he has to say. Hi again. I keep thinking about the confidence interval for our graduate salaries you sent me, estimating the mean to be between $111,000 and $127,000. Are you able to check if more than half of our placed graduates earn at least $100,000? That could be a huge promotional piece to publish. And I think a 5% risk of publishing if it turns out to be false is fine. Alright, so let's look at the key objectives here. Number 1, calculate the proportion of placed graduates that earn at least $100,000. 2, check if the central limit theorem applies. 3, select the right type of hypothesis test. So is it a two-tailed test or a one-tailed test to the right or to the left? State the null and alternative hypotheses, set the significance level, calculate the test statistic for the sample, calculate the p-value for the test statistic, and then draw a conclusion from the test. So we're really starting to put everything together here. Good luck. Time to get into hypothesis tests for the difference between two populations, starting with dependent samples. So you can make hypothesis tests for dependent samples by calculating the difference from each pair of observations in the samples and then treating the difference as one population. And this is the same exact thing that we did for confidence intervals with dependent samples. So if we wanted to do a test on the mean difference between the undergrad grades and the MBA grades, we can create a new column with the difference. Because these are dependent samples, we have the MBA grade and the undergrad grade for the same student in each observation. And now that we have this difference, well then we can do a single population hypothesis test on this new variable. Now, pro tip, do a two-tailed test with a null hypothesis of the mean difference being equal to 0 if you want to check if there is any significant difference in the means of the samples. Or you can do a one-tailed test if you want to check if one is greater than the other. Now you can do this with 0 as well, or use another number if you want to test a different magnitude of difference. Maybe you want to check if you have sufficient evidence to prove that the MBA grades in this case are at least 5 points higher on average than the undergrad grades. Alright, time to put you on the spot with an assignment on hypothesis tests with dependent samples. We just got an email from Tommy Test, the head of admissions, so let's see what he has to say on employability improvements. Hi, I spoke with Nick and he mentioned that he's confident that we can build in a 50-point improvement on employability scores into our recruitment process. And I just want to double check that it's not an incorrect assumption to make. Do you think you could run a quick test? Honestly, it's not a huge deal. So unless you're really confident that it's not the case, I'll just stick to his number. Thanks and nice to finally speak to you. Alright, so key objectives. Number 1, calculate the difference between the dependent samples. Number 2, calculate the sample mean and standard deviation from the difference. Number 3, state the null and alternative hypotheses. Set the significance level. Calculate the test statistic. Calculate the p-value. And then draw a conclusion from the test. And by now you should already know how to do these calculations really well, but the trick here is to frame the hypotheses correctly and set a significance level that aligns with Tommy's email, which I'm confident that you will. We just covered dependent samples, so time to talk about independent samples. Again, just like in confidence intervals, hypothesis tests for independent samples have two key calculation differences. The standard error in the test statistic uses the variance and the sample size from both samples, and the degrees of freedom for the p-value also consider the sample variances, so it's no longer just the sample size minus 1. So this is the formula for the test statistic, which is the same as always, just with those minor differences. So in the numerator, you have the difference between the sample means, and then you subtract the hypothesized difference in population means, and then just divide by the standard error. And if we look at the p-value calculation, we'll still use t.dist, but for the degrees of freedom, again, instead of doing n-1, we'll use this formula, which we already saw for the confidence intervals for independent samples. So we already know how to calculate this and how to make it easier on ourselves by using Excel. But that's it. All the other steps in the hypothesis test are exactly the same. Alright, time for the final assignment of the section. Tommy's back with another email, so let's check it out. I took a quick look at the salary data for our first batch of graduates, and it looks like those with previous work experience are earning a bit more on average. Can we assume that this will always be the case? If so, we may have to start screening some applicants based on this. I don't want to potentially impact our student numbers on a hunch though, so let's only take a 1% risk. Alright, so key objectives here. Calculate the mean and variance from both samples. Calculate the difference in sample means. State the null and alternative hypotheses. Set the significance level. Calculate the test statistic. Calculate the degrees of freedom. Calculate the p-value. And then draw a conclusion from the test. So it seems like a lot of steps, but really we're just running a hypothesis test, same as always, with those minor calculation differences that come with independent samples. So good luck. Alright, time for the key takeaways from this section on hypothesis tests. Number 1, hypothesis tests let you evaluate assumptions about a population by using sample statistics. So the null hypothesis is the assumption to evaluate, and the alternative hypothesis is any other possibility. And the important thing to keep in mind is that you're not actually looking to confirm this assumption. This null hypothesis is already the status quo. You're just testing to see if it's wrong, in which case you'd want to change this status quo. And that's why it's so important in decision making. You're saying, I'm happy doing things this way, assuming my assumption is true, but let's just test to see if it's not true, because if it turns out that there's enough evidence that my assumption was wrong, well then I want to do things differently. Now, number 2, the significance level sets the threshold for sufficient evidence. When you don't have all the data on a population, which is usually the case in real life, then you'll never be 100% sure of anything, except for the fact that you don't know everything. So what the significance level does is draw a probability line that says, if a sample is at least this improbable, then the assumption I made in my null hypothesis is wrong, and I'm happy to accept the alternative. Now, the lower the significance level, then the lower the chance of making a type 1 error, which is rejecting a true null hypothesis. But keep in mind that this also increases the chances of a type 2 error, which is failing to reject a false null hypothesis. So there's always going to be a trade-off here, but the key is to think about which type of error is more acceptable in each situation. Finally, the p-value is the probability of the sample fitting the assumption. So if it's greater than the significance level and it doesn't cross that probability line, well then you don't have sufficient evidence to reject the assumption or null hypothesis. So just keep doing business as usual. If it's less than the significance level though, and it does cross that probability line, well then you reject the null hypothesis and assume that the alternative is true, likely causing you to make some data-driven changes or decisions.